A new topic today, multi-level logic optimization is in some ways a generalization. More degrees of freedom here than in two level, because you could do everything that you are doing in two level minimization, but there is also the opportunity to have as many levels as you want in the logic. So, this problem is in general more difficult than the two level logic optimization problem. Of course, our objectives are also different here for the optimization. Here too, as you would expect, an exact optimization is difficult, it is computationally complex. So, some heuristics are employed, and overall one can group these heuristics into two different phases. The first phase is an optimization using generic gates. Generic gates means that we do not necessarily take into account the detailed physical properties of the gates in terms of area or timing and so on, but just treat these as generic two input NAND gates and OR gates and so on. And the optimization is done in terms of those generic gates in the first phase. In the second phase, there is a technology specific mapping, that you take the optimized netlist from the first phase and then make decisions about how that generic netlist would be realized in terms of cells that are available in a particular technology library. So, this is where the target architecture, the target library and so on, all of those come into the picture. But the first phase, we just try to perform a number of optimizations, just keeping high level objectives like literal count, for example, in mind. So, we will look at both of these in that order. The first phase would be a generic optimization, in which if it is multi-level logic, you may be looking at just literals, for example.
Are the generic gates change when we give a different library input? I mean, does the tool prepare depending on, for example, in my library that I am going to give for technology mapping does not contain certain kind of AOIs or some other complex gate,
Right.
then would the generic gate list change or it remains same?
You may pre-process it, essentially a replacement process would have to be done for some set of gates in the generic to one or more gates in the actual technology library. So, even if a particular gate is not available, a combination of the gates from the generic netlist would be available in terms of implementing by a combination of gates in the technology library. The generic netlist might still be the same, but we are yeah, it is independent of what is coming later on. Here too you could argue that ideally you should do them together, but it is just the complexity of the engineering that leads us to divide it into two phases.
Actually, what I meant was read the library, find the functions that are supported in the library, use them as generic.
Yeah, but it is very unlikely that there are functions in the generic library that are not implementable in the real library. Of course, the whole point of designing a library is that you want it to be suitable for all kinds of purposes. So, what are the chances that you will not have a NAND gate? Once you have a NAND gate, everything is realizable in terms of that NAND gate. So, the issue of course is that there may be many different ways of realizing the same logical function, and therefore, we need to know all the details in terms of 5 different drive strengths that may be available. So, maybe 5 different gates do the same thing, but the properties are different in terms of area and delay trade offs. But those numbers, what is the area, what is the delay of a particular gate, we do not take into account in the initial phase when we are just dealing with generic gates in a generic netlist. Okay, you start with the representation. These are logic networks that are composed here. So, a graph returns as a natural choice. We had actually dropped the graph structure for the 2 level just because it was a more specific structure, some tabular representations were used there. But now that you have any number of levels, the graph again is suitable. What do the nodes represent? They could represent some local functions where there could be multiple inputs and a single output usually. So, it could be a function like this. So, that is a node into which there are 3 incoming edges, each of A, B and C may be a primary input, or it could also be the output of some other node, some other function, and the output here would be a single edge. If that y is connected to many different nodes, then you would have different edges from that node to all the other nodes, all of them having the value of y. So, that is what in general this is, it is a local function. It could also represent a primary input or a primary output. We will look at an example soon. But what are the edges? Edges represent nets in the design, wires in the design, with the assumption that this is a single source, single destination, which is a sort of a breaking of the abstraction of the meaning of a wire. In general, you could have multiple sources if you design it properly, but nevertheless, a single wire is a single structure which is broken up in the representation into multiple edges, all with the same source, but multiple destinations like that. Right. All of this is the same physical wire, but the way to use a normal graph representation and through that perform all the traversals and optimizations and so on is to make this assumption, break up that wire into multiple edges. Of course, you know that this is not the only way to compose a graph. You could have hyper edges in a graph that could actually connect multiple nodes. That could be the more correct way of representing wires in general. For most of these optimizations, it may not make too much difference, but actually when it comes to a later phase of physical synthesis, that is where that representation is more important. This particular approximation usually does not hurt the optimizations at this level of abstraction, but it does make a difference when it comes to routing, for example. There too this assumption is made, but that assumption may interfere in some ways with the quality of the result. But here it is an easier assumption, we just say that if the same wire is connecting one source and multiple destinations, then there are different edges from that node to all the other nodes. Let us look at an example here. This is a graph that represents a logic network. What you have here are the primary inputs. These are nodes in this graph. These are the primary outputs, those are also nodes. The whole thing could be just a combinational function, and I have some nodes that are primary inputs and primary outputs, but in general a node represents a local function like this. So, I have P equals C E plus D E in one of the stages, and that is one node here. It has inputs C, D and E. So, these are the edges that are connecting C, D and E to that node, and there is one output. Yes, so each node is performing one Boolean function. So, that is the output. That other node there performs the function r equals p plus a prime. P comes from the output of that node there, and a prime comes from that node, original node itself. That is the general structure. So, there is no limit to how complex that local function could be. It could be a large function, but the representation of that could be a two level function in the general. If it were multi-level, then you would have the different levels being abstracted out into different nodes in the structure. Okay. For such kind of representation, let us see what is the relationship between area and delay. In two level logic, minimizing the size of the cover, which is what our objective was, remember, it minimizes area. Of course, there is a straightforward relationship between the number of implicants we are including in the cover and the size of the circuit. What about delay? Remember, this was a PLA structure with an AND plane and an OR plane. I had my inputs and I had outputs. This was the general structure. The optimization objective was to reduce the number of rows I had in the PLA, with the implication that now each row counts as some additional area overhead. Remember, the number of connections do not count towards area, right. That is just the way we have designed this, designed the fabric itself. What about delay? Number of connections has an impact, but it is a sort of a secondary impact. Does this number of implicants, which determines area directly, also determine delay?
In PLA, no.
No, not at all, or
so to realize the more number of applicants, there will be more number of
Area.
each single unit which will have its own delay. Area will, so
what do you mean each single unit? We have a bunch of functions f1, f2, and these are my inputs x1, x2, x3 and so on. There is a bunch of inputs and these are the bunch of functions. So, let us assume that we are realizing one PLA, whatever the number of functions, we still have one PLA structure. So, I want to know what is the critical path through this structure. All of this is still a combinational logic, right. There is no sequential element there. If you have a sequential element, it is outside, like we had in the case of the state machine. Where is the critical path through this structure? It is hard to answer that without showing where the connections are, because the connections are making a difference, but assume that the connections are uniformly distributed or they are there everywhere. So, for now, if you remove the effect of the connections, the question is, does the number of implicants have an effect or it has no effect on the critical path through the PLA?
Connections are all there, then no difference should be there, because all the
All of
ending
them are
is
computed in
parallel and all the ORing is also computed in.
Okay, but can we go beyond the gates and look in terms of wires? Because they also contribute to delay, right?
So, more the number of rows we have, delay would be more.
Why?
The vertical delay will increase.
The vertical distance increases. The path is likely to be something like this, this and this. That might be the longest path to the design. What happens in the gates is an additional effect that does need to be taken into account, but you can see that if you arbitrarily increase the number of implicants, then this path gets longer and longer. Right. At some point, it would begin to dominate our delay through the structure.
This is just the wire delay.
Just the wire delay, yes.
There are no like capacitance involved which take the most part of the delay calculations.
How is the wire delay computed?
The load on the gate, so there must be a gate in the AND plane. Its delay will depend on the wire
Right, right.
load. So that's what.
You could refine each of these. This critical path dependence is not an exact formulation, as you can see. It's hard to determine the critical path if I don't tell you anything about the connections. But if I assume that the connections are what they are, then and they follow some kind of uniform distribution, then this certainly is one orthogonal effect. But it simplifies one of the things, which is this is not a bad optimization objective even for delay. We argued in terms of area primarily as we developed the theory, but in fact you could also use it as an objective for delay minimization. So, in general you may expect this kind of a curve that represents an area delay trade off in two level logic, because a smaller area could actually mean smaller delay and a larger area could mean larger delay. In multi-level logic, that is certainly not the case. Area could still be estimated by the number of literals using the argument that we have seen earlier. Essentially, each extra literal results in extra gate or transistors. Right? It is like if you had, instead of 2 elements, if you had 3 elements in a cube, then the NAND gate corresponding to the realization of that product would have 2 more transistors, 1 N transistor and 1 P transistor. So, in terms of multi-level logic, if I am going to count the number of transistors, then the literal count is actually a reasonable estimate. Delay though is a completely different argument. How do you find delay in a multi-level logic network? Delay corresponds to what? It corresponds to the critical path. Of course, I should be computing the critical path. What dependence does that have on the number of literals in the circuit?
So one question previous.
Yeah.
So when we go from rig layout to when we select it with a particular library, do we also consider things like a 4 input AND gate versus two input AND gates? Or
Yeah, but that is the topic of the next phase. So, why don't we wait until that? Idea is I should be able to evaluate all the possibilities I have and choose the best one.
Just quick question. Just,
Yeah.
the generic for NAND is n input NAND in the synthesis tool. It's not only a 2 input NAND or a 3. It's an n input.
You could assume it to be a 2 input NAND. It's all right. But again,
What is the norm? I was
norm is 2 input.
Norm is 2 input.
But then I know that if I have a 3 input that's available, then I can realize it in terms of something. The critical path computation, if you have some logic here, some bunch of inputs and some bunch of outputs, this is a multi-level structure, not this structure, but it is a multi-level structure. Is there a dependence between the number of literals, which in some ways is a measure of the area complexity of this design, versus the critical path? In general, actually it is hard to say anything about it. You could have structures like these, right? These are disconnected structures. There are paths from here to there, there are paths from here to there, there are paths from here to this. You are essentially computing the longest path from any input to any output. That in a graph structure in general has nothing to do with the number of nodes of the graph. Right. So, you may expect an area delay trade off that looks like this. There might be a trade off that you spend some more area and generate a circuit in which the delay is actually smaller. We have seen examples of this. What are examples of circuits you have already seen that go too far? In fact, the adder designs that you have seen, they are a perfect example of this. the simplest adder in terms of area is which one? The ripple carry structure is a very small and compact design, but that is not the best in terms of timing. There are other structures that are actually more efficient in terms of timing, but the trade off is that the area is larger. Like if you compare a carry look ahead adder, for example, it is larger in area than the simple adder. So, there is this kind of a trade off that usually multi-level logic would exhibit. You can see that in general, suppose I have this kind of a function, this node, the node A is reused, which is a good idea in general from an area point of view, because that output from here is leading to some function here and some other function here, and certainly we do not want to recompute A twice, it is the same function. So, from an area point of view, this sharing makes perfect sense. What about alternatively if I did this? There is some redundancy in this structure because you have duplicated the logic, but could this be good from any point of view?
Faster.
It could be faster. Why?
The fan out.
Yes, that fan out here causes larger load to be driven by whatever is the gate that is driving the output of A.
You get more opportunity to restructure A and B and A and C together.
Yeah, each of them independently could be optimized separately. Maybe you will find some opportunity for further, but even this simple argument shows that some redundancy actually might help us arrive at a faster circuit. Okay, the optimization strategies for multi-level logic effectively are a bunch of transformations, just like a set of operations that we had defined for two-level logic. Each of them could be a stepwise improvement that essentially preserves the I/O behavior of the circuit, but internally we are trying out different possibilities for the nodes, structuring of the nodes and the edges, until there is no further improvement in terms of perhaps the number of literals, if it is an area optimization that we are trying. These could be rule based, which means that essentially it is a pattern matching and a replacement. You have a pattern or you have a bunch of patterns that you already know could be realized in terms of more efficient patterns. You are searching for those patterns, and when you find them, you are replacing it by the more efficient patterns. That is all effectively that is happening there. You have a question? Yeah.
Rules are predefined by us? Or
Yeah, it's defined by us. Yeah. But this can be a lot more complex. To start with, we seed those library of patterns, a library of pair of patterns with the most elementary rules of Boolean logic, but it could be more and more complex based on our experience, based on ultimately maybe in a later stage on the knowledge of the target library even, but this could be a large number of patterns, but we will look at some of them. This in general could be the search for a graph, a subgraph in our larger graph and replacing it by some other graph. But even though that graph isomorphism is what would be the algorithm that would help us identify that, and we already said that it is a difficult problem, but these patterns may not be very complicated. It may be that the number of nodes here is actually very small. So, you could afford to have a little more exhaustive kind of pattern matching strategies, because the subgraphs are not large. Let us take a look at a bunch of these transformations. Again, each of them independently is actually very simple. The one called elimination, in which we just remove a node. Removing a node means replace its occurrences in the network by the expression that corresponds to that function. So, the idea is to remove that node from the graph. So, if I remove that node, then that output is being used here. So, I need to replace the r by whatever was the function that corresponds to r. As you can see, this is a low level analogy of what optimization, what transformation that we have already seen.
Function inlining.
Yes, this is just an inlining equivalent of an inline. This is also a function. These are Boolean functions, and the appearance of that literal r here on the right hand side, wherever it is going, would lead to replacement of that literal by the function that it corresponds to. So, structurally it would lead to dropping of a node, but also adjusting of the input edges into wherever that node is going. So, this node now has additional edges. Why would we do this? Does it affect the number of cubes?
We are not assuming the nodes are optimized.
Yeah, this is again a local transformation. This is a routine that could be called many number of times. By itself, what does it achieve? Question of course is that does it take us towards our optimization goal, which is minimizing the number of literals. That is what I would do. What literals are there in this circuit, in the initial circuit and the final circuit?
That are eliminated.
R is being eliminated, and that leads to a reduction in the number of literals. Is there an increase because of some other reason, because of the elimination?
Pin node now has 3 inputs.
Yeah.
But R is the letter, actually A, B, C, D are the letters.
A, B, C, D are the literals. R is also a literal. This is multi-level logic, and what does this R anyway? This is like an OR gate, and it does perform some Boolean function. The output of that is going into that other node, which will also be realized in terms of some gates. There R is a literal because it is an input to that gate.
Can you think of this as well? So with function inlining here, what we have achieved is now the last node has 3 literals rather than 2 literals.
Yes.
But if I look at the previous picture, there I had 3 gates to realize this.
No, number of literals have reduced in any case. So, in a way, it is
This leads to increase or decrease in the number of literals in the general case?
decrease.
Decrease.
At one node they have increased and one node I have eliminated.
Right. So, in general case, what might happen?
It may remain same, you are saying. But
No, in the
The
general.
which would be needed probably is reduced. Like we need to store R's value somewhere.
This is purely combinational logic. If R has to be stored somewhere, that happens in a separate thing. This is just an intermediate output of a gate, of a combinational gate, and it is going into another combinational gate.
there are 8
Right. That is why the question was not what happens here, but what happens in the general case.
sense.
Notice this is plural. Plural means this may have many outgoing edges. It will increase. In general, it must increase. What is happening is one occurrence of that function is dropped, but many occurrences are added. So, why is it useful? If it is increasing, then it is taking us away from the desired optimal target. But the reason it is worth doing it is that in the process you have a bigger expression. It is likely that the original expression there was too small to afford any further optimization. But if you actually absorb it, earlier we actually looked at this in the context of that just what we discussed. If in a bigger expression there are more opportunities hopefully for finding optimizations, but in a much smaller one it may be difficult.
And also from multi-level logic perspective, now let's say this bar was on critical path, right?
Right.
So if that is the case, then we have reduced one node in our graph. So if I consider each as one node,
We're
and
not
let's
looking
say
at
this was
timing
a
yet.
critical path.
Are we looking at timing yet?
This reduction of the literals is a timing optimization or a area optimization. Yeah, we just argued that actually literal count is not a faithful objective if it is a timing optimization.
Removing node, I optimize both.
Here in this particular case there is no difference in timing. It depends on what the target gates are, but what you have there is there is an output, there is an OR gate if you ignore the literal, and there is another OR gate that corresponds to the third one. The first one is CE plus DE, whatever that is, that is not changing, and I had P here, I had R here, I had S here. This could be the ultimate realization in terms of logic. But in the transformed one, what we are saying is this part is, the P part is unchanged, and I now have a 3 input OR gate, perhaps. Not very different in terms of the timing behavior either. Remember, we are still talking about generic gates here, we are not talking about picking up elements from a technology library, but it is not hard to anticipate that you submit this to a technology mapping phase. If there is a 3 input OR gate in the library that is better than 2 cascaded 2 input OR gates, we would definitely discover it and replace it by essentially this. This particular example, there is really no difference in timing. Yeah.
Argument which we made, like for the literals, we don't focus on timing. That is
right. Literal count is not a good measure of timing.
But typically, when we will look at a real problem, then we will look at all the aspects, right?
Yeah.
Delay, power, area, everything.
Yeah.
So then these are, where does this literal transformation comes in the whole flow? So first we start with.
The optimization objectives are different, as you know, it would take, if it is area and you want to focus only on literals, that takes you in one direction. If it is delay, then it may take you in a very different direction, but you have to inform the optimization tool in some way about the mix of area versus, both of these are weighted in some ways in terms of priority, and similarly the direction that it takes for optimization would be influenced by those priorities.
So from tool perspective, at the end of that moving,
the tool may take a very minimal input from the user. It may be, if it is an area versus delay optimization, it may just take, for example, just one fraction, says how much priority, what percent area is 50-50 is how I should be doing my exploration, or 40-60 or whatever. It wants to simplify the interface to the user, and therefore it may do that. Alternatively, it might also actually expose some of the functionalities as individual optimizations that could be turned on or off, if you want to go into more detail of that.
how mature and good are industry tools in this?
Oh, they are very good.
Do people even make optimizations after tool makes that, or it's good enough? It's at a
Do
maturity level?
designers interfere manually with the results of optimization tool? Yeah, they do all the time, it is done, but I think after decades of commercial use, they are mostly trusted. You might still make changes, but it is a reasonably mature technology, I think. We are not able to discuss all of those in a course like this, in which there are only a couple of hours on complex optimization like this. What we are reading about obviously here is the very basic set of steps. These would certainly be done, whatever we are studying here, they would certainly be part of more complex routines, but the routines have evolved in a direction of essentially knowledge of the patterns from previous designs and populating those tools with more and more intelligence about what are the patterns to look for and what makes sense. The generic arguments are not very different, but they are tuned in various ways by specific observations that are kind of messy from a theoretical point of view, but conceptually they are fine. We are looking at pairs of patterns, and you could grow that set of pairs to anticipate all kinds of effects and learn from earlier experiences of optimization.
Don't give the opportunity to the end user to add more patterns.
Tool may not give the end user the opportunity. However, the tool itself incorporates a number of such learnings from previous. The EDA vendor of course is exposed to large example designs that they get all the time, and they try to optimize, and designer says that this is my expectation and the tool is not meeting it. You can see that you can hack it by introducing some pattern, and it's all right if it is done from the tool vendor's side, but still it's a reasonably sophisticated list of patterns. Perhaps we can't interfere with it as users, but they are there anyway, and those that set is likely growing as and when new things are discovered that the tool is not doing well at.
Is there an opportunity of a learning based scheme in here? I mean, instead of going to a cycle,
they evolved by way of heuristics and simple lookup and replacements. Perhaps by now it would be more formal. So that learning has always been happening, it's just that we are not calling it learning. Right. But now we can call it learning. Yeah, that's what, now we can call it machine learning, but they refer to intelligence otherwise that designers have had and tools have always had. Yeah, we can call it machine learning. Today it would all be called machine learning. You could make that learning process customized to a particular
not
use.
Otherwise you have to wait for 9 months. They don't give enhancements so easily.
The thing is that particular tailoring that you are doing in one context may not work in a different context.
That is okay.
That's why it makes sense to expose it in some ways to a particular design environment. For my library it makes sense, so I will use it. So there is an argument in favor of that level of customization indeed. Okay, let's move on to the next transformation. We will try to put these together in one small algorithm later on, but we are just looking at these transformations independently. Okay, decomposition refers to replacing of a node by two or more nodes. This is if I have a complex expression, I can try to realize it in terms of simple expressions. This is the other way around. This also may make sense in certain contexts. So, splitting a complex function, why would you split it? It may lead to the identification later on of common sub-expressions between this node and some other node. I have an expression like this. Part of this we can see that there is a factorization possibility. Factorization is good in multi-level logic because it reduces the number of literals, of course. So, I could realize this bigger function in terms of this expression, which is the first node. You have the product of that with D, which is this, and that part remain unchanged. This too could be thought of as an intermediate step, but in general factorization is always good. It helps us reduce the number of literals. Extraction is the name given to this common sub-expression elimination transformation. It leads to simplification in terms of the number of literals. If you had something like that, this could be realized in terms of those factors. a bigger expression like that could be realized in terms of some factors like that, then you can identify that these two factors are actually the same, that is the same sub expression, and therefore I could restructure my graph to have C plus D computation first, introduce a new C plus D computation, but that output could be used to generate P by a product with E and a different function T that also uses K. Of course, as part of all of this, I can also do our normal two-level logic minimization. Within an expression, within one node, we can always invoke a two-level logic minimization tool that would take whatever that expression is and try to come up with a simpler one. Substitution would be replacing an expression in terms of other nodes. What we have here is, I have A plus, so this part of it is the same, but doing a factorization, we realized that the A plus B is actually common. I could replace that by K times A plus B, for example. Then I can, instead of recreating that function K A, K B, I have not shown all the edges here. This one has the K, but it also has A and B as inputs there. But since Q is already computing A plus B, I can then realize this in terms of Q. So that would result in the creation of a new dependency, because you are expressing one node in terms of the output of a new node, but it could also lead to dropping of some dependencies, because you now do not have the A and B feeding into that node, you have only K, Q and E feeding into the node.
How is this different from CSE?
It is in general not different, but this is a simpler operation than CSE.
Cost-wise.
Yeah, CSE, remember we are finding any sub expression in one node and noticing that that sub expression is there buried in a different node. But here we are just trying to express one node in terms of the output of a different node. So this is an easier optimization to perform. Anyway, if I did all of those in some right order, then if that was my original circuit, I can count the number of literals that are there. The number of literals would be the count of all of these literals on the right hand side of the expression. And my final circuit would look like this. It all looks very clean and much smaller, looks more efficient, but that is because it is a small circuit and we were able to do that. But in general, our optimization strategy would consist of a bunch of routines that we would call that hopefully take us towards the optimum. Of course, we can run it until there is no further improvement, and that would be the local minimum that we are looking for. So we won't be able to go into too much detail here, but let us just quickly look at some of the simpler algorithms like an elimination algorithm. That was the first one that we looked at, and remember, the elimination in the general case leads to an increase in the literal count. It is like inlining increasing the number of operations that we are doing. To the elimination algorithm, we somehow have to guide it by saying how much you are allowed to increase the literal count by, because this may be very expensive. If it turns out that there is one function that is used in a large number of other nodes, then we should not be performing that elimination. This leads to an increase, so we would like to control it in some way. That algorithm can actually take a number like 10% or 5% or something like that and say that you can increase, but only by this much, not much more than that. So if I have one node, let us compute the cost of the elimination in terms of number of literals. I have one node with L literals, okay, and there are n occurrences of R in different nodes. Those are the sites where we could perform this inlining. Right? If we eliminate the R from all of these, then that would lead to this p plus a prime getting duplicated into all of these. Right. So, in general, if this expression has L literals and there are n occurrences of R, so those are the places where we can eliminate that R from. Can we quickly quantify what is the difference in terms of number of literals for the whole circuit? How many more literals are there because of the elimination? First of all, I am getting rid of n occurrences of R, which means that each of them is of size L, right. That is what is getting in, right. I have p plus a prime occurring in a number of places, that is a size, and the number of this is n times it is occurring. So, that counts as an increase, but there are some decreases that are also happening. The R was of course there earlier, and that R is dropped now. So, how many R's are dropped?
3.
Yeah, n of them are dropped. So, that is one reduction. Anything else is dropped? Yeah, this block is dropped, right. Remember, this block is dropped. So, L I can drop also from this. That could be my expression for computing the cost of the elimination of one node. I just have to see how many outgoing edges are there and what is the literal count of this node. So, extra literals are these that would have to be compared with how much we are allowed to expand it by, which could be an input to the elimination algorithm. This is my graph G, and K is the increase in literal count that we can tolerate per node that is eliminated, but it could be in general a percentage or something like that. So, you just repeat the following. Select a node with the val which is that cost computation less than or equal to k. If that cost is exceeding k, then do not eliminate, otherwise you do the elimination. Here this just refers to if it is a node V3 or something, then if there is nothing further to eliminate, then you return, but otherwise you replace that node x by the logic function that corresponds to that node everywhere in the logic network where x occurs. And the algorithm is simple. After that, you just repeat the process until there is nothing further to do. This is a relatively simplistic computation here, just saying it is less than or equal to k. It could be that you define this not on a per node basis, but for the entire network. When you are about to exceed the total k that you are allowed to expand by, then you can just stop the algorithm. That is a simple strategy. Let us look at one representation. So, in the process of these transformations, we would have to worry about the representations. We pointed out graphically what those operations were, whether it is elimination or extraction, substitution and so on. How do you perform that in general? There has to be some simplification, some kind of representation that you would have to use. it turns out that the general algebraic model is often used as an approximation of the Boolean algebraic model, which is what we want to perform here. This is like a division operation that you want to perform, right. For example, that substitution where you are trying to see whether one node could be expressed in terms of another, you are trying to perform a division operation. Division is not so difficult in general algebra. There are of course tools for us that can perform that efficiently. Doing it in Boolean algebra is a little trickier, and actually what could be used is just a variation of the same algebraic model. We do understand how to perform division automatically in a generic algebraic model. We could just reuse it. Reusing it means that some of the Boolean algebra rules that are additional would have to be ignored. For example, all of these things about complement do not make sense in real algebra, right. This is a Boolean algebra specific. But if I use those algorithms for performing my manipulation, then it means that I can't exploit complementation and its associated simplifications. We would just have to treat A prime as a different literal from A. Okay. If you have to do that, you can't use rules like this, you can't use rules like this, but you also can't use simplifications like these, because A times A is not A in other algebras. In Boolean algebra it turns out to be the case. And the idea of don't care of course is not there in those algebras. And nevertheless it is okay, it is just that the correctness is not interfered with. You may have something that is not necessarily the most efficient, but the rules of algebra can certainly be used because they are applicable here. It is just that Boolean algebra has a few more rules. Let us quickly go through one representation and the implementation of a division operation. It seems very simple conceptually, but you do have to go through some steps to make sure it can happen properly. You do need an efficient implementation here, and let us quickly define some terms and then define division and then quickly go through how you would perform division. It is not difficult, but you do have to go through a certain set of steps. Let us define a support set of a cube to be the set of variables in that cube. Okay. So, ABC is the cube means the set of ABC is the support set defined for a cube. So, we say F is a divisor of D if I can express D in terms of this. You say F times some quotient plus some remainder, where F is not null and Q is also not null. We will also have the support set of F and the support set of Q being disjoint. This is the division that I am trying to perform, AB plus AC plus BC plus AD. That expression is being divided by A plus B. I should get C plus D. That is true in Boolean algebra, it is also true in other algebras. But if I have a rule like this, right, you divide this by A plus D, you should actually get A plus B, it is okay in Boolean algebra, but this will not be discovered by this standard division algorithm, because in other algebras that is not necessarily true. This is merely a matter of notation, but let us keep this in mind anyway, so that we can actually come up with an algorithm for division. Two expressions are there and you are trying to divide one expression by the other expression. You can regard an expression as just a set of cubes. This is a two-level logic we are talking about. Each of the individual nodes has essentially a two-level logic function, right. So, let us say I have an expression like this, it consists of that set of cubes. So, you can regard that expression as the set of cubes. CA1 means that the set of cubes for expression A, the first cube is AC, the second one is BC, and so on. And if I have a different expression A plus B, then the set of cubes here is A and B, and CB1 would be A and CB2 would be B. Okay. So, this is just a notation which will help me later on when I actually perform the division. So, my divide algorithm, which essentially divides A by B, can be in general the following. For k equals 1 to nb, where nb is the number of cubes in B, A is divided by B here, right. So, what are we doing? We are going through all the cubes I have in the set B. I collect first those cubes of A that satisfy this relationship. Support set of that cube of A is a superset of this support set of the kth cube of B. What is this doing? Suppose this was A and B was something like that, then it's picking one of these cubes of A, it's already picked the kth cube of B, and it is checking whether this support set is a superset of this support set. In other words, what is it doing? Whether one is divisible by the other, one cube is divisible by the other, that is all that it is doing. It is written in a way that looks very mathematically impressive, but there is not much happening there really. Okay, if D equals null, then return null A. What does it mean? If you can't find a cube, then null A means it's returning the quotient and the remainder. Right? Quotient is null and the remainder is A. Right. So this is more like some humor in this algorithm that we can try and recognize. Otherwise, if it is not null, then we are doing this. By now you can get the joke perhaps. Qk equals D by support set of CBk. What would this be doing? D is the set of all the cubes that are divisible by the kth cube of B. All of those we picked up, and divided by essentially is saying that if it is AB and A, you remove this and you keep B. If there were multiple here, then you remove A from all of them. We are picking up only those terms that are actually divisible. Right. So, I would be left with B and C. So, that would be the quotient for the ith cube. So, that is all right. So, I picked up the quotient Qk. If this is the first time, then I will say Q equals Qk, this is an initialization. But if it is the second iteration or the third iteration, then I am doing an intersection of what is already there with what is there from previous iterations with what I just computed in the current iteration. What is the point of that? It is like saying I had C plus D earlier, but now it turns out that for the kth cube I have just C, then I should take an intersection of these two, which means that C should remain. So, it is not C plus D, the plus D part of it is gone, but only C should remain. We will quickly go through a different example, but this is just the algorithm. The point of discussing it in this way is just to show that not much is there in this algorithm. At the end of this, when do you stop? The loop is over all the cubes of B. Okay, so, that is what the k is iterating over. At the end, whatever has been maintained in Q, that is returned as the quotient, and the remainder that is returned is essentially you multiply Q by B. Those terms of A that are not there in this, they are returned as the remainder. Okay, we should be able to quickly look at this with an example here. if that is my A and that is my B, the algorithm I promise is the same as the other one, although you have to do a graph isomorphism or something to check. So, k equals 1, that is the first cube. Which one would we pick up? This B. So, we are iterating through the cubes of B. A is being divided by B, so we are taking the cubes one at a time and dividing A essentially. So, if k equals 1, then what is D? What would I pick up for D? These are those cubes of A that are divisible by the first cube of B, which is
AC, BC, AD. First three.
first 3. Why? Only AC and AD. These are the ones that have an A in them. That cube that you have picked up from B should be a subset of, so it should be AC and AD. If D equals null, then you return null, so it is not. What do I get for QK here? Right, it will be CD. It's a division, right? I am removing the first cube. Here that first cube is A. Okay, so that's my QK, and since k equals 1, that's my current cube, okay, C and D. Of course, algebraically you can see that as of now, C plus D could be a possible quotient, because if you multiply that by A, you are actually getting at least part of that expression. So, that is the first iteration. Second iteration, k equals 2, I get what is the corresponding CBK, that is B, right. So, I would get BC and BD, all of those terms, all of those cubes of A that are divisible by B, those I would pick up. Now, when I divide that by the support set of this, I would essentially be dropping the B's and I would get CD. This CD is then intersected with whatever I had maintained earlier, and that is still CD. So, that is the end. There are only 2 cubes in B. So, I am out of this with the Q being CD and R being E. Does that make sense? Is that an expected quotient and remainder for this division? Yeah. Basically, we are saying that A can be expressed as A plus B times C plus D. E is the odd one out, so that is the remainder. What if it was slightly different? Let us say like this, then so these were my terms. B is, though the first cube is not just one little, but it is a bigger cube, it is AX. Then I do the same thing. What do I pick up in my first iteration? All of these terms that have an AX in them, those would be picked up. These are the 2 terms that would be picked up, and the Q1 would be C and D, because I would drop AX now from them. So, that is good. That is my first iteration. Second one, for k equals 2, the cube is B. So, the D would now be whichever ones have a B in them, right, that one and this one. So, that is this. C and XD are my second QK. Now, I want to perform an intersection that leaves only C. Does that make sense?
Yes, sir.
It's an expected thing. So, that is the end of the loop, and I have as remainder, it is a bigger remainder now. Essentially, you are saying this is AX plus B times C plus remainder. There are some terms that are not divisible, and that is okay. Okay. This is just the general algorithm for performing division. There is actually nothing Boolean algebra specific in this division. This is just a regular division algorithm. This process could be made a little more efficient in the following way. We have some more information about this process. Now, where is the opportunity for optimizing? We want to divide one node by another. Potentially, there are n square such division, there are a large number of such divisions to check in that substitution algorithm to find whether we can replace one or whether we can realize one node in terms of another node. So, because that would be a large number of trials, you also expect that most of these or many of these in general would be null. Many of the divisions in the general case they might be null. Why? What are conditions which are actually very frequently occurring in a general logic network where you expect the division to not really go through?
In the paths from the primary inputs till
Yes.
you reach certain nodes, if they are completely disjoint, not able to define it.
Yeah, we can realize some in terms of path, but before that one expression is being divided by another expression, right, and so some expression is being divided by some other, this is A being divided by B, and we want to see whether I have a q times B plus some remainder. As it turns out, there are a number of elementary checks that can help us prune this search space. You do not have to do it, a quick look at these two expressions can actually tell us that the division cannot be successful. What would it be? Informally, can you think of some such? Yes, this looked like a joke, but it is actually something we can start off with. If B has even one variable that is not there in A, then that division cannot go through, because when you come to that here, when you come to the D here in this example, you will get null. If even one of those quotients results in null, then the intersection is null and the division does not go through. You could actually enumerate many such rules. Not just it does not have a variable, but if it has a cube, just generalizing this, whose support set is not a subset of any of the cubes of A, then also that division cannot possibly go through, right. If I have an AC and I do not have an AC as a subset of any of those cubes, then also it cannot go through. I can actually come up with quite a few such rules. If the number of terms here is 3 and that is more than the number of terms of A, then also it can't. This is just a small set of these rules. They are useful, they help us not go through that cumbersome division process unnecessarily and finding out in a later iteration that the quotient is actually null. So, count of a variable in B if that is greater than in A. What is the meaning here? You take there are two A's here, but there is only one A in this. So, yeah, the many such rules could be there. There is one from a path point of view, since you mentioned it, we can say one thing. There is a function associated with each of these nodes, right, if that is my Fi. Okay, function associated with K is Fk. So, if a path exists from node I to node K, then what can I say about divisibility between Fi and Fk? This is a path, just through that logic network there is a path between a node to another node. This is very common, right. What divisibility relationships we can expect if there is a path? Or let us say I tried to divide K by I, looking at the first and the last one, or I try to divide I by K.
I by k will be null
Why?
Because K will have n.
Yes, right. If there is a path from I to K, then function corresponding to Fi divided by function corresponding to K, that would be null. You can easily see that. Look at whatever is the previous node, the literal corresponding to that node is there in K, but it is not there in I. It is true even if this is just the immediate predecessor, then too that relationship holds. Of course, because this is the case, that function Fk by Fi might be okay, but Fi by Fk would not be there because you do not expect cycles in this graph anyway. Okay, so with these I can have a substitute algorithm that looks like that. That is my graph of vertices and edges for all pairs, and we could still have all pairs, but what we are doing is we are quickly getting rid of many of those pairs in this. So, if A is the set of cubes in Fi, B is a set of cubes in Fk, you perform a filtering for the null quotient of the kind that we saw. So, all those rules you could actually apply and check whether you can just filter out that division. If it is passing, then you can go ahead and obtain the quotient and the remainder by actually applying the division algorithm. But these rules are very simple, so you do not have to perform the division, which might actually be a more expensive operation in general. Okay, so, if you have a non-null quotient and that substitution is actually favorable, that favorable is left ambiguous there. In the general case, it could be that you quantify it in some way, in the sense that some other parameters could actually influence whether you would go ahead with it or not. Then you can substitute Fi by whatever is the function for k, and so you have a quotient and the remainder. Yeah.
If we have filtered for null quotient, why are we checking that q not equal to phi again?
That filter is not an exhaustive filter. If we establish that path is there, then it is null, but it does not mean that if the path is not there, then it is not null. Right. This is just one simple check that definitely tells us that there is no need to divide, but you can still divide and find that it is null. Yeah. Okay, that is all that is there. Obviously, we did not cover all of the multi-level logic optimization. This was just that substitute algorithm, but some of these are related. This division could be used as part of, as a sub routine in some of the other algorithms also. But that is the extent to which I wanted to cover the first phase of the multi-level logic optimization, which is independent of the technology library. The second stage would be the technology mapping, where now we have an optimized netlist, but that netlist is a generic netlist. We did not take care of any particular physical properties of the library elements. That we can do in the second phase.